Have you ever looked at a map on your phone and just thought of it as a snapshot of the past? Like a static recording of what a place looked like at one very specific moment in time? Well, what happens when a map becomes a living, thinking entity? What happens when it actively paints itself in real time, literally observing and predicting the very world around it? Welcome to The Explainer. Today we're diving into a massive, absolute game changer of a paradigm shift in how we understand our physical world.
We're going to unpack the fascinating merging of artificial intelligence and geography into a continual living system. Because this isn't just about finding the fastest route to the local coffee shop or looking at satellite images of your roof anymore. It's about an incredibly powerful concept called continual monitoring. This is where AI observes the Earth, from the sheer vastness of space all the way down to the temporary obstacles in your living room in real time, constantly learning and adapting on the fly.
Here's our roadmap for today. First, we'll look at the evolution of maps. Second, the rise of GeoAI. Third, continual monitoring on a macro scale. Fourth, navigating spaces at the micro level. And finally, the ethical tightrope. Let's jump right into Section 1, the evolution of maps, from cave walls to living systems.
Cartography has always been a reflection of exactly what society needs at any given moment, and it's totally driven by the technology of the day. Over 13,000 years ago, humans were carving prehistoric maps into the Abans cave in Spain just to understand and survive their immediate local surroundings. Fast forward a bit to the age of discovery in the 15th century, and society's new demands for global trade pushed us to create highly accurate paper maps using early, painstaking surveying techniques. By the late 20th century, we had a totally new problem. We had way too much data and needed to automate spatial analysis, which gave birth to Digital Geographic Information Systems, or GIS. But today, in the 2020s, we've officially entered the era of generative AI. Just think about that shift for a second. We aren't just digitally recording geographic data anymore. We're using AI to hallucinate and generate entirely new geographic insights instantly.
That brings us to Section 2, the rise of GeoAI, where AI meets geography.
We've reached this pivotal tipping point where artificial intelligence is no longer just a neat experimental feature tacked onto mapping software. It is the core workflow. The source material defines GeoAI perfectly here. It's the integration of artificial intelligence with spatial data, science, and geospatial technology to improve our understanding and solve complex spatial problems. To put that into perspective for you, it's taking massive amounts of raw data from satellites or LiDAR sensors, data that would honestly take human analysts multiple lifetimes to parse through, and processing it at an unimaginable scale, practically instantly.
So the crucial takeaway here is this major transition to what we call the living map. Because AI can process all of this visual and spatial data in the blink of an eye, maps are no longer those static snapshots of the past we grew up with. By streaming endless historical layers of data into sophisticated deep learning models, these systems are continually updating. They don't just explain what happened yesterday anymore, they actually forecast what's coming next. This isn't just mapping, this is continual monitoring in action.
Let's zoom out for Section 3, continual monitoring on the Earth-scale canvas.
So how does GeoAI actually monitor our entire planet from space? Well, the applications of continual monitoring at the Earth scale are vast and absolutely critical. Satellites and high-altitude drones equipped with multispectral sensors feed their visual data straight into AI algorithms. And this fundamentally changes how we handle something like real-time disaster response. In the event of a sudden catastrophic flood, AI doesn't just show us where the water is, it instantly analyzes the local terrain to predict exactly where the water is going to spread next. That means emergency crews can evacuate the right neighborhoods before it's too late. It's also used heavily for border security to detect unauthorized crossings in super remote areas and for environmental tracking, spotting illegal deforestation or stealthy mining activities deep in protected nature reserves the very second they happen. It lets us track long-term landscape evolution completely autonomously. No boots on the ground required.
The way this works behind the scenes is pretty wild. A deep neural network architecture extracts that kind of vital information from space by taking raw, messy satellite images, pre-processing them, and feeding them into a complex deep learning model. This model learns the spatial and semantic features needed to identify a region of interest, basically distinguishing a man-made rooftop from, say, a flat rock. But it doesn't stop there. It then uses a boundary extraction network to regularize those noisy, pixelated shapes into neat, usable architectural footprint polygons. It literally takes messy, real-world pixels and turns them into precise mathematical data, automatically, continually, day after day.
Now let's shrink things way down for Section 4, Navigating Spaces, the Indoor Challenge.
If AI can monitor a shifting forest or a spreading flood from space, how on earth does it navigate the changing obstacles in a single, ordinary room? This requires continual monitoring on a micro scale. Think about the space you're in right now. It changes constantly, right? Chairs get moved, doors open and close, people walk through. If you want a robot vacuum, you know exactly how easily autonomous systems get completely confused by a simple misplaced shoe. For a critical autonomous system, like a smart wheelchair navigating a busy hospital ward, the map has to be forever evolving. It relies on a technology called SLAM, simultaneous localization and mapping. The system has to figure out exactly where it is in the world while simultaneously updating the map of its ever-changing surroundings.
On one hand, you have the highly complex theoretical math driving these autonomous wheelchairs. You've got frame data coming from a camera, feeding into specialized OpenVS SLAM software, parsing keyframes, and rigorously calculating paths. It's a ton of logic. But on the other hand, what the AI actually sees and uses to navigate the real world is something called an occupancy grid map, or OGM. It translates all that complex math into a simple grid. The green areas are safe, navigable paths, and the blue areas represent hard obstacles. By continually updating this grid frame by frame, the system adapts to the reality of a busy room in real time.
And to make sure it doesn't hit anything newly placed in the room, like a cart that just rolled out of a doorway, the system relies on LiDAR raycasting. Imagine invisible lasers shooting out in a wide 90-degree arc right in front of the vehicle. When a ray hits an obstacle, it stops, telling the deep learning model exactly how far away that sudden object is. The AI processes this instantaneously to adjust its trajectory, entirely avoiding the obstacle and calculating a safe path to get back on track. It's this beautiful, continuous loop of perception and action, happening dozens of times every single second.
Which leads us to our final section, the ethical tightrope and the cost of an always-watching AI. An environment that is continually monitored and mapped by AI naturally brings up some profound philosophical and privacy challenges. There's a really stark contrast between traditional mapping and geo-AI. Traditional cartography is deeply rule-based, it's transparent, and it's highly traceable. If a mapmaker draws a line, you can find out exactly what historical data they used and what mathematical rules they followed to put it there. AI-generated maps, though, they act as a complex black box. They are incredibly difficult to unpack and explain. If the AI hallucinates a road that simply isn't there, you can't easily trace exactly why the neural network made that specific mistake. And in scenarios involving critical urban planning or emergency response, that lack of accountability is a massive, real-world problem.
The sources outline several specific risks we really have to navigate as this becomes the norm. Beyond those hallucinations, there's the risk of biased training data skewing spatial analysis entirely, copyright infringement from the massive datasets used to train these models, and serious reproducibility issues. But perhaps the most pressing concern for everyday people is privacy. A massive geo-AI foundation model, which is trained on vast amounts of internet imagery and census data, might inadvertently memorize incredibly sensitive personal locations. It's theoretically possible that a vision language model could learn the exact alignment between a specific building and its residents, disclosing private home addresses to anyone who simply prompts the AI with a photo of the building. Let that sink in for a moment. As geo-AI scales up, securing these foundation models against these kinds of continuous privacy breaches is absolutely paramount.
All of this leaves us with a pretty profound thought to wrap up this explainer. The big takeaway here is that we are no longer just passively reading maps, we are actively being read by them. From tracking massive global environmental shifts to steering a wheelchair safely across a crowded room, continual monitoring is totally transforming our spatial reality. But as our world is continuously painted and repainted by AI, what is our place within this living map? Thank you for exploring with us today. Keep questioning and keep learning.